Hi everyone. Today we're going to focus on worksheet problems. So I do encourage you to at least watch through the first example because it's worksheet problem 2 and I don't have the solution available for you on the key. But if you want to skip the rest of the video and just consult the key, that's okay. All right, so for worksheet problem 2, we're asked to sketch a voltaic cell, also known as a galvanic cell, for each redox reaction. So we want to label the anode and cathode and indicate the half reaction that occurs at each electrode. And then we also want to identify the species present in each solution. Also, we want to indicate the direction of electron flow. So there's a lot of stuff we're going to do. So we have two reactions down below, and it looks like some of them are balanced, but some might not be balanced. Okay. Although that doesn't really matter too much for what we're doing today. All right, so we've got our first reaction where nickel ions are reacting with magnesium to produce nickel and magnesium ions. Okay, so again, the first thing we always want to do is figure out what's being oxidized, what's being reduced. So let's assign some oxidation numbers. So nickel is an ion to start, so its oxidation number is the same as its charge. Magnesium is neutral. Nickel in the products is neutral, and then the magnesium ions in the products have a +2 oxidation number. Okay, so is nickel, oh, I went way too far. Is nickel gaining or losing electrons? So it is gaining electrons because it's becoming less positive. So this would be oxidation or reduction? Reduction. What about magnesium? Magnesium has an oxidation number of 0 to start and then +2 at the end. So is it gaining or losing electrons? So it's losing electrons. So is it being oxidized or reduced? Oxidized. Okay, so we have our two half reactions. So now let's identify which half reaction will be at the anode and which will be at the cathode. So is the reduction half reaction at the anode or the cathode? The cathode. And then what about the oxidation half reaction? Is that at the anode or the cathode? The anode. That's the only one left, right? Okay, now typically we draw the anode on the left-hand side. So we could label the left cell the anode, and then the right-hand half cell will be the cathode. Okay, so now let's write the half reaction that occurs for each. So at the anode, we have our oxidation reaction. So magnesium is losing electrons to become magnesium 2+. And then at the cathode, we have our reduction half reaction. So nickel ions are gaining electrons to become pure nickel. And I'm just leaving out the states because they take up a lot of room. All right, so on the anode side, our electrode will be made of magnesium. So we'll have a magnesium metal strip there. And then we'll have some sort of solution with magnesium ions in it. So that could be magnesium nitrate, for instance. And then on the right-hand side, we'll use nickel as our electrode. And then we'll have a solution with some nickel ions floating around. So now, are electrons traveling left to right or right to left? So magnesium is losing electrons and nickel is gaining electrons. So electrons are going to move away from magnesium and towards nickel. Okay, and then this tube here is our salt bridge. All right, so now let's look at the second reaction. And let's assign some oxidation numbers. So we have hydrogen ions reacting with pure iron, which will produce hydrogen gas and iron ions. All right, so hydrogen initially has a +1 charge, so its oxidation number is +1. Iron is neutral. And then in the products, hydrogen gas is neutral. It's in its elemental form. And iron is +3. Okay, so hydrogen, we're going from +1 to 0. So is hydrogen losing or gaining electrons? Gaining electrons. So that would be reduction. Okay, and then what about iron? Iron is experiencing oxidation. Okay, so does reduction go with the anode or the cathode? The cathode. And does oxidation go with the anode or the cathode? The anode. All right, so now let's label our diagram below. So again, the anode will go on the left side, the cathode will go on the right, and let's write out our half reactions for each. So the anode is the oxidation half reaction, so we've got iron, and that is losing electrons to become iron 3+. All right, and then the cathode, we have 2 hydrogen ions, and they're gaining 2 electrons to become hydrogen gas. All right, so this isn't really balanced because the 3 electrons don't match up with the 2 electrons in those reactions, but we're mostly just concerned with what goes where, so don't worry too much about it right now. All right, so on the left-hand side, we will use iron as our electrode, and we'll have some iron ions floating around in solution. Now on the right-hand side, we're going to need a special electrode because we don't have a metal that's made of hydrogen, right? Hydrogen's a non-metal. So what we're going to use is platinum connected to a hydrogen tube. And then in solution, we'll use some sort of acid so that we're generating hydrogen ions. So probably hydrochloric acid. So then where are electrons traveling to and from? So are they going towards the right or towards the left? So electrons are traveling towards the right because remember, iron is losing electrons, so they're leaving that system and they're going over to the right, the cathode. All right, it's not too bad. And if you're a visual person, this is probably a lot of fun because you get to actually draw stuff. If you're more of a math person, don't worry, math is in your future. All right, so now for worksheet problem 3, we're going to calculate the standard cell potential. So remember that's E cell for each of the electrochemical cells in problem 2. Okay, so we've already done half the work. These are the same reactions we just saw. And for A, remember we said that nickel was being reduced. So it was gaining electrons, and then we said magnesium was losing electrons to become magnesium ions. All right, so we already said nickel was reduced, which means it was the cathode. And then we said magnesium was being oxidized, which means it was the anode. So now if you want to pause the video and look up the potential values for each of these half reactions, you can do so. Okay, so for nickel, the potential value is negative 0.23, and everything is in units of volts. For magnesium, the value is negative 2.37 volts. So remember, our equation for E cell is equal to the potential of the cathode minus the potential of the anode. All right, so the cathode was nickel, so we'll put in negative 0.23 volts. And then we're going to subtract negative 2.37 volts, the anode. So this will end up as negative 0.23 plus 2.37. So that should give us a value of 2.14 volts. So, extra question, is this spontaneous or non-spontaneous? So E cell is positive, which means it's spontaneous. All right, so that's good. We drew the correct electrochemical cell in the last problem, right? We didn't have to flip it, so that works out. Oh, I guess I gave myself a slide already to work on that, so we'll just go to B. All right, so for B, we already said that the hydrogen ions were, let's see, where are my notes? Those were reduced. So the hydrogen ions gained electrons. And then we said that iron was oxidized. So it lost electrons. So again, you'll notice the electrons here don't balance out, but that's okay because remember, even if we multiply these reactions in order to, or multiply them by a factor in order to get the electrons to match so we can cancel them, we still don't change the potential value. The potential value stays the same. Okay, so let's look up these potential values, and again, those are in units of volts. So for the hydrogen half reaction, remember that's our standard hydrogen electrode, so we set that equal to 0 volts. So super easy. And then for iron, this is a little tricky because remember, iron can become either a +2 ion or a +3 ion. So make sure you're looking up the correct value and the correct half reaction. So for this particular half reaction, where iron becomes iron 3+, the value is negative 0.036 volts. So that should be just right below the hydrogen reaction on the table 19.1. All right, so now we're just going to plug in what we already calculated before. So we're going to take the cathode potential and subtract the anode potential. So which one is the cathode? What did we say earlier? So the first half reaction, right? So we're going to put 0 volts there. And then we're going to subtract negative 0.036 volts. So that will just give us positive 0.036 volts. All right, so is this spontaneous or non-spontaneous? So this is spontaneous. So we did write that in the correct way. All right. Okay, so now for worksheet problem 4. Let's make a sketch of the voltaic cell represented by the line notation below. Write the overall balanced equation for the reaction and calculate E cell. Okay, so we have our cell notation down below. And remember that the left-hand side represents the anode. Okay, so in my notes, I see. Okay. So then on the right-hand side, that represents the cathode. And that makes sense because manganese is losing electrons, so it's being oxidized, which is the anode. And then we've got this chlorite, I believe it's called, chlorite ion, and it's losing electrons to become chlorine dioxide. And notice that neither of those states are solid, so we have to use an inert electrode, and we'll use platinum. Okay, so let's sketch out our cell. So we know that manganese, or the anode, is on the left, and the cathode is on the right. Now manganese is found as a solid, so we can just use pure manganese as our electrode. And then in the solution, we just have manganese 2+ floating around. And then on the right-hand side, we said we were using platinum as our electrode. And then we have some chlorite floating around in solution. And then we've got some gas just bubbling up. Now, are electrons going from the left to the right or from the right to the left? From the left to the right. So that's pretty standard. Okay, so now we're asked to write the overall balanced equation and calculate E cell. Okay, so manganese, we said, becomes manganese 2+. And how many electrons will it lose in that process? 2. Okay, and then for our other half reaction, let's see, we said that ClO2 minus, let's go back. So that was at the cathode, so it's being reduced. Oh, so I actually said the wrong thing there. So ClO2 is going to gain an electron to become ClO2 minus. So I might have misspoken before. Okay, so the reason that I knew that it was going to gain an electron is because, remember, this side is the cathode. So that means it's being reduced, which means that it's gaining electrons. Okay, so we need to make sure that this is balanced. So we need to make sure our electrons equal each other for each half reaction. So in the first half reaction, we have 2 electrons. In the second one, we have only 1. So what can we do to make sure those balance? So we're going to multiply the second reaction by 2. And I'm just going to rewrite that and make it a little bit easier. So let's just put some 2's in front of everything. Ta-da! All right, so now we can balance and write our overall reaction. So we can cancel our electrons, and we've got manganese, which is a solid, plus 2ClO2, which is a gas. And then that's going to end up as manganese 2 plus, which is aqueous, and 2ClO2 minus, which is aqueous. Oh, not Ag, Aq. All right. So now let's look up the E values, so the potential values for each half reaction, so we can calculate E cell. So in table 19.1, we would find that the E value, or the potential, for the manganese half reaction is negative 1.18 volts. And then for chlorite, let's see, that's 0.95 volts. Okay, so now we're going to plug that into our E cell equation, where we take the potential of the cathode and subtract the potential of the anode. All right, so which one was the cathode again? Manganese or chlorite? The chlorite. So we would put that first. And that means manganese is the anode. So we're going to subtract negative 1.18. Okay, so I'm going to plug this into my calculator real quick. 0.95 plus 1.18. So we should get a value of 2.13 volts. So is this spontaneous or non-spontaneous? It's positive, so it's spontaneous, which works out because we already drew our diagram, so it's a good thing it's spontaneous. Okay. So I'm skipping problem 5 for now because it's going to be more relevant in our next lecture. But I do encourage you to go over worksheet problem 6 on your own. So in this problem, you're going to calculate E cell for each balanced redox reaction. So they're already balanced, so don't worry about that. And you're going to determine if the reaction is spontaneous as written. So once you calculate E cell, if it's positive, then that means that the reaction is spontaneous. But if it's negative, that means it's non-spontaneous, and you have to flip the reaction to make it spontaneous. Or another way to think of it is that the reverse reaction is spontaneous. All right, so if you do need help with that, the worksheet key is on the Canvas website, or you can always ask me questions through email or in office hours.